Hey guys, Mr. Backwork here. In this video, we're going to look at the derivative of the arcsecant. So as we're looking at finding the derivative for y equals the inverse secant of x, we need to make sure that we're dealing with x values whose absolute value is greater than 1. And the reason why is, as we look at the graph of the inverse secant, it's not defined between -1 and +1. It's only defined to the left of -1 and to the right of +1. So the absolute value of x has to be greater than 1 in order for us to be able to do this derivative. Now, if we want to go through and do it like we've done our other ones, we're going to first rewrite this using what we know about inverses. So if y equals the inverse secant of x, then the secant of y is equal to x. And we're going to differentiate this using implicit differentiation. So if we take the derivative of the left-hand side, the secant of y derives into the secant of y times the tangent of y, but because we just differentiated something with a y variable in it, we have to attach that dy dx, and then on the right hand side, if we differentiate that x, we get 1. I want to solve to get dy dx alone, so I'm going to divide both the secant and the tangent over to the right hand side. So this is going to say dy dx is equal to 1 over the secant of y times the tangent of y. Now we want things written in terms of x. We know that the secant of y is equal to x, so I can replace that first part with just a regular x, but in order to replace this tangent, we're going to have to bring in a trig identity. There is a Pythagorean identity that says tangent squared of your variable is equal to the secant squared of that variable minus 1. So if I want to solve to get the tangent alone, I would have to square root both sides. So I get the tangent of y equals, now on the right hand side, when we square root that, it's got to be plus or minus the square root of the secant squared of y minus 1. And again, I'm going to do some substitution with that secant of y. We know that secant of y is x, so I can really rewrite this as x squared minus 1 underneath that radical. Now, as we're plugging that in for this tangent of y down here, I'm going to pull that plus and minus out to the front of my fraction, and I'm going to leave the square root of x squared minus 1 on the bottom of the fraction with the x. Now, ideally, we would want to do something with that plus and that minus, because having that in there, there's kind of some ambiguity as to what our answer is going to be. So if we look at the graph, what I want you to notice is that the slopes of each piece of our graph, it's always pointing up, so the slope is always positive. So what we can do in order to get rid of the ambiguity with the plus and the minus in there is we can do the absolute value of this first x in here, which will help us eliminate that plus and that minus. We don't have to worry about the x underneath the radical, because as we're looking at this, our function is only defined outside of -1 and +1. So if we square those things and then subtract 1 from that, we're always going to get a positive value underneath that radical. So the only x that has some sign ambiguity in it is that first one. So that's the one that we would need to do the absolute value of. So then our final derivative here, this says dy dx is equal to 1 over the absolute value of x times the square root of x squared minus 1. Now, just like our other trig functions, we're not always going to be dealing with a plain inverse secant of x. So if you've got the equation y equals the inverse secant of some differentiable function u, then as you're using this formula, you would also have to include some chain rule information. So y prime would be 1 over the absolute value of u times the square root of u squared minus 1, but then we would have to attach whatever the derivative of that inner u thing is within that inverse secant function. So in this example, we're going to look at finding the derivative of the inverse secant of 5x to the 4th. So we can see that we've got an inner function within our inverse secant, so we are going to have to do some chain rule stuff. So as we're doing this derivative, we're going to do 1 over the absolute value of that u thing, so that's our 5x to the 4th, and then we have a square root and then we're supposed to square whatever that u thing is. So we have to take 5x to the 4th squared. We have to subtract 1 from that. But then because of this inner function in here, we have to attach the derivative of that inside piece. So if we drop that 4 down as a multiplier to the 5, that turns into a 20x, and then we have to subtract 1 from the power, so that turns into x cubed. Now, because we're multiplying, I'm going to take this 20x cubed and put it over 1. When we multiply the numerators together, we just get 20x cubed. And then on the bottom, there's actually a little bit of cleanup work that we can do here. This 5 is a positive 5. And when you take something and raise it to an even power, that's always going to end up being a positive value in here. So these absolute value bars aren't going to have any impact on this 5x to the 4th. So we're just going to pull that out of our absolute value. And then underneath our radical, we can simplify down that 5x to the 4th squared into 25x to the 8th. But then we still have that minus 1 underneath there. We can do some reducing with the 20 and the 5. So we get 4 on top. We can also do some reducing with the x cubed and the x to the 4th. So we're going to get a plain x on bottom, along with that radical having the 25x to the 8th minus 1 underneath it. That's going to be it for this video. Thanks for watching.